Thanks for joining. This demo showcases a hybrid GPU-CPU pipeline for high-throughput signal processing. It combines NVIDIA Cuda libraries, or SDK, for batched fast Fourier transform acceleration, as well as a comparison, the Intel MKL for optimized CPU side transform. So we'll be comparing GPU and CPU. So it'll focus on three areas. One is the architecture, how the project works. It's using memory map files for file handling and chunk orchestration and then device selection. And then we're going to focus on performance, comparative benchmarks across both libraries, including latency and throughput matrix. And then I have some integrated logging and post-run analytics. The goal is to demonstrate a reproducible, scalable workflow, that leverages both platforms for maximum efficiency. And I'm using relatively speaking, a lot of data for just a desktop. It's each fast Fourier transform runs a gigabyte worth of floating point data. So I use real data. Basically what I did is I hooked up three microcontrollers, STM32F4 series, and had some port listeners that captured the packet, so to speak, and wrote them out to memory map files. And so then I just kept doing that until I had a gigabyte worth of data. Now, so that you don't have to do that, I have included a couple zip files in the project. They're called memmaps1.zip and memmaps2.zip, and you just extract them into one directory. Anyway, I'll give you the steps on how to do it in the README, and we'll walk through it. The point is, you won't have a gigabyte worth of memory, worth of data, but you will have 8 files of 16 meg apiece. So you get an idea of what it is without having to gather it yourself. So I'm using Python for a lot of the post-processing. And I'm using Visual Studio. I've done a lot of demos using Linux, and so Visual Studio is the first class citizen here, and it's pretty easy to set up. The Cuda SDK installs Visual Studio packages, so to speak. So anyway, let's talk about the machine that we're running on. It's an Intel Ultra 7 with 32 gigabyte of DDR5 RAM, a NVMe SSD storage, and an NVIDIA GeForce RTX 4060 GPU. The GPU is using NVIDIA Studio drivers. They're 12.9 compatible. And then I use the NVIDIA app to set it to auto tune, so it scans for optimal performance, and you can monitor the performance also to see to get your utilization, your CPU utilization and your GPU utilization. And I will tell you that once I've tweaked this project, I got spikes up to over like 67% GPU utilization. And also I have some reports, some Matplotlib type reports that I'll show you at the end that gather all types of telemetry and performance data. I will mention it's this script here, packet_forward.py. All you have to do is set it to the right port on Windows, COM3, COM4, whatever your microcontroller uses, and it will write out the memory map files if you want to do that. Now, I did contribute some slides as a fast Fourier transform reference section. Not going to go over that here. It's a brief overview of how the voltage signals are interpreted in the frequency domain using FFT. And so these are included for reference, and the slides are checked in as slides.pdf or just a slide, so you can take a look at those. So it covers voltage over time. Anyway, I find myself wanting to explain everything, but I'm just going to go through these slides, show it to you. Talked about fast Fourier transform, how it transforms a time domain of like raw voltage off the microcontroller. That there's the clock driven, gets you digital samples, converted from a analog, where it's converted into a frequency domain, tells you all the presence of different frequencies in your signal. And then I give you a graph here, and this is simulated. But I have all of that explained in the notes part of the slides. This is my bibliography. This is from my library, what I've learned about it. I actually found this middle one, this old Sedgwick book. I went through it, and it breaks it down pretty good. Okay, so when you install the Cuda SDK, you'll get this NVIDIA app. You can use it to view your performance here in this performance tab. Like CPU utilization and GPU utilization are very interesting. And so I selected auto tune. And so when you do that, it scans your system, comes up with these values. Anyway, so that's how you tweak. I don't have the most powerful GPU in the world, but it's good enough. And so anyway, I set auto tune. So I'll actually show you how to set up the project, but before that, just explain the setup, Cuda versus MKL. So MKL is by Intel. It is for Intel processors. It takes advantage of its architecture, its SIMD, its AVX, and all of that, versus Cuda, which takes advantage of your GPU. And so I have a dual path fast Fourier implementation. I run them together. We benchmark them together. And so I'm comparing throughput, latency, resource usage, and the performance trade-offs. And in a nutshell, in the smaller chunk sizes, what I mean by chunk. So a chunk is how many floating point numbers that we push through the fast Fourier transform at once, like an array. And so in the smaller chunks, like 128 floats or up to like 4096, and when you MKL benefits a lot from that and kind of kicks Cuda's butt. Cuda has a lot of overhead. It has a logic kernel, and also it has this host device wall where you're creating your user data and you have to copy it over onto the device. And you would think that you can operate in the device domain, but I did not find. I found performance degradation instead of increases. So I think I'm doing the best practices for how to prep your data and pass it into the GPU device. However, where Cuda shines is where the chunk sizes increase. And so I have here I'll show you that real quick. So I have this enumeration or pseudo enumeration of how many floats to pass in. So I have this loop here. And so it's looping through the chunk sizes, and then I'm calling Cuda fast for FFT and then MKL FFT, and the chunk sizes are increment in size. So it starts at 8192 floats, then 32768, then 65536, up to 1,000,000 floats. And so Cuda really starts to overtake MKL, and I have graphs and results for that you can run after the run. And my reports for performance are program-wide, so it's just not run per run, it's for the whole program. So I can do this. I can run this 5, 6, 10, 20 times, and the report's going to gather everything from the entire program, not just per run. Okay, so we're in the project properties, and let's go to all configurations. And you can see that it's a little, I'm sorry, the font is very small, but in a normal Visual Studio project, C++ project, we have VC directories. Well, there's also this Cuda C++ because you're compiling with the CUDA compiler is the compiler for the device code, and your code is compiled by the by the MSVC compiler. And so the one thing is that when you install the CUDA SDK and select the Visual Studio components, like the plugins, they put in the include and libpass and the libs for you. You don't, in fact, you're not able to edit them. You can look at them in the project files. So I'm not sure I like that. I think I like to be able to add my own include and my own libs. But anyway, they do that. So you don't have to do anything except install the CUDA SDK, and it will configure CUDA for Visual Studio C++ project. And you have to choose that project type in when you're starting a new project. However, for MKL, I do have the include path, and you find it. I have them hard coded here. You can say project, or well, wait. You can use a variable, right? But C program files is pretty universal here. But so that's where Intel One API MKL latest include. That's what the include is, and then you go to library directories, and yeah, C program files x86 Intel One API MKL latest lib. And then in terms of, then you go to linker input to actually specify the libraries. And by the way, you do ignore libraries or you're going to get some errors. Lib CMT, you just ignore that across all configurations. It's just a warning. It'll still build otherwise, but I don't like warnings. So then, okay, so additional dependencies, and here we go. Edit that, and here's the list. So here's the MKL libs here. I don't need the space in there. I should add, I think my README has which ones to add. The cuft.lib, or it's cu CUDA FFT.libs, what that stands for. CUDA ART static lib. Those were added by the CUDA SDK, but it's these three: MKL underscore Intel underscore LP64.lib, MKL underscore core.lib, and MKL underscore sequential.lib. You have to add those, specify those. And I believe I have that in the README. Cancel. So that's how you set it up. So we separate telemetry from performance for a very simple reason, that telemetry degrades the performance. You're logging, you're measuring, and all of that. And so they're two separate paths. So telemetry ensures that the captured data is valid, complete, not malformed. And so we decouple the two. So we want to maintain high performance, so we report them separately. And the way we control it is through conditional compilation. So I'll show you the code. By the way, this is the main, and it's in a .cu. So this is the domain of the device or the GPU. And then FTT wrapper.cpp, that's the domain of the host. This is my code. And so here's our defines that if you want telemetry, you run with that flag enabled. If you want to make sure that your FFT results are legit, then you log MKL or define log CUDA, and it will print out your floats after post FFT processing. So make sure that they're not all 0 or something, right? And we'll talk about some of this other stuff, but those are the main things, is that when you run the program, so like MKL underscore FFT. Now I've chosen structured programming, so they run as functions with helper functions, but I do have some structs and classes for supporting it. I didn't make it too object-oriented. I kept it more structural, more of a flat hierarchy. And so I do use a signal report class, but I only instantiate it when log telemetry is enabled. And the same thing down here. If log telemetry is enabled, we get a whole bunch of information basically related to the magnitude of the range of the chunk of the float chunks. And then here we go, we log if this is defined. And again, telemetry. Now for the perf, we just go ahead and always log it for perf because it's after it's done. The time part of the run is over, so we just dump to the perf log down here. And the same thing with the Cuda underscore FFT. And there is more duplicated code than I want in these two functions, but I'm pretty satisfied with where it is. And so again, the data that we're processing, it resides on the file system as memory map files. So these are in-memory type files, but we don't load them all and start reading them all at once. You know, it's a 1 gigabyte. So a program, you know, it would overwhelm the heap. So what we do though is we put them all in one directory. That's kind of a requirement. And then it uses the file system object, std file system, and walks the directory. I mean, if you had subdirectories, it would walk those too. But, you know, for better performance, you want to keep them flat. So I have 65 or so of these memory map files in one directory. And they're 16 meg each. And so what the program does is, before I was just walking it, opening it, reading it, feeding it to FFT, but I got a perf gain by opening them all at once. And by the way, I count that. That's in the timing. I didn't cheat and put it outside the timing. This is all part of it. And so we go ahead and iterate all the files, get the handles, get the mapping, get the pointer to the data. We don't start reading it. Then after we get all of that, we start another loop and we range through a vector full of these map pointers with the file handles and so on. And then also this file mapper class, we use RAII. So here I'll show that to you in code too. So we really only have two classes. We have the struct file mapping, and this is what gets stored in a vector. So it stores the handle to the file mapping, and a pointer to the mapped data and its size. And the destructor, so let's say you're iterating through the directory and you're storing these handles in the file mapping and the data pointer. Then when you're done with that, you start iterating through. Here, I'll show you that. So here's our main function. The first thing we do is we instantiate a std vector of file mapping called mapped_files. Then we start the timing. Then we get some smart pointers ready. Now here we are. We're going through the file system. And you have to make sure that your mapdir, I have it hard coded in main. Okay, here let me take you there real quick. Yeah, so make sure that this matches where your memory map files are. I keep mine right in the directory, right next to main.c, or right next to kernel.cu. But you can put them wherever you want. But this memmapdir, you pass it. You pass it to the function. It's the first, and then you pass a chunk size. Anyway, back to the code in MKL_FFT. So it iterates the file system that you pointed to, the mapdir, and then it gets the string, the file name, and creates a file path. Then it instantiates a file mapping object that you get from this open map file which is above. I'll take you to that real quick. So when you call open map file, you pass it the string name of the file path. It does a create. It's checking to see if you succeed. Then it gets a file mapping based off of that and closes the file. Gets a file mapping of it, closes if it errors. So it has this error chain where I return a default constructor of file mapping. Then it gets the file size, so it helps to pre-allocate. And then it gets a view, and that is the data, this void star mapped. And so at the very end, it instantiates a file mapping object. It saves the file handle, it saves the mapping handle, and saves the actual data and the file size. So now we have, and so getting back to the loop, oops. So we're iterating through the file system. We're getting the string of the file name. Then we call open map file, passing back a file mapping that we just saw save the handle, the mapping handle, the size, and the pointer to the actual data. So we have a pointer to the actual data that we're saving in this object that gets pushed onto a std vector. So we have an array basically of these objects of handle, maps, and the pointer basically. So then we close out. We looped it through and we store this vector of handles and pointers. Then we have a range loop iterating through this vector. And so what we do is we get a data pointer and we're preparing it. We're preparing it to populate a chunk. The chunk is the size passed in that I showed you in that enumeration. That starts at 4096 all the way up to 1,000,000. And it's going to populate this smart pointer called voltage with the chunk size of floats. And then, so we have this, then we are going to interleave it. So this is not getting the data yet, right? It's we're getting this. We're preparing an array for the FFT call itself, and it takes your raw numbers are the real. It's a complex number that consists of a real number and an imaginary number. And so what you do to prepare for FFT is you pass your voltage, your actual voltage value at the raw value is the real number, and then you get it ready by just passing in 0.0f floating value, and then FFT is going to refactor both of those. And now it's getting ready for the call. MKL uses these descriptor handles, and these are all initialization type routines. And then finally, this compute forward is actually the routine that performs the FFT, and then this deletes it, the descriptors, all the scaffolding that supports it. So then we, if we have telemetry enabled, we write to the telemetry log, and if we want to see the data post FFT, we have a log MKL and so on, and then we wrap up the timing and wrap up the perf. And so that's how it works basically. So we try to get a pretty decent perf game by file handle queuing, and so as I said, it as this vector goes out of scope that holds all of the file mappings, then the file mapping class cleans up after itself when a vector calls the destructor of every one of its elements, and so these destructors are cleaning up all of the Windows file handles for you. You don't have to explicitly call close. It's doing it here as the vector goes out of scope, and as part of it going out of scope, it iterates all of the elements, calls all the elements destructors, and it cleans up. So here's a diagram that shows you how it works, how we're queuing, constructing, chunking, queuing, and so on. Okay, now I'll give a demo of how we, the workflow of getting these benchmarks. I guess the first one will be, well, we'll go with Perf first, and then we'll do telemetry. So I start with opening 2 instances of PowerShell, and I navigate to the project folder, and I have a pip env that is specific to this directory to run all of my Python scripts. And I have in the README, it shows you what modules you need to import using pip import. So the first thing we do is I have a monitoring app that monitors GPU and CPU and produces a graph. Now it waits for the executable to start. So Python, so on the right hand is the monitor. Okay, so it's waiting, and so here it is here. And so we're looping through and increasing the chunk size each time we do a run, alternating Cuda and MKL runs. So there'll be 10 runs total, 5 Cuda and 5 MKL. And it's almost finished. So we'll just wait. Okay, so it's done. And you see that the monitoring app stopped by itself. And so now we run Python benchmark. And here's what it gives us. So the blue is the Cuda, the orange is the MKL, and you can see in the horizontal axis here is chunk size. So you see as the more floats we pump through FFT, the more throughput Cuda gets. And it sort of works the opposite way with MKL. MKL works best with smaller sample sets. You can see that it does better with under 5,000 than Cuda, but then Cuda sort of passes it up here at about the 8, around this area here. So throughput is basically the lack of bottlenecks, and it just pushes through. And with Cuda, the bigger that, well, up to a certain point, there's a diminishing returns, but I go all the way up to 1 million floats, and you can see that that is the best timing. We're only logging up to 300,000 here, but and then latency is another way of looking at it. You can see that the latency drops the more bigger the chunks become. Then compute performance. Again, Cuda is just increasing the bigger the chunks are. Now this last is a totally different matrix. That's nothing to. It's just system utilization. So the blue line is the RAM. The RAM kind of stays consistent. The red is the CPU. You can see the CPU stays kind of consistent in terms of percentage of use of the CPU. But then the GPU, you see these big spikes. So remember, we're alternating between Cuda run, MKL run, Cuda run, MKL run. It's almost 1-to-1. And you can see that the bigger the chunks, the more that is utilized. So when we get to that last run of 1 million floats, it's all the way up here. I saw it 67% when I watched it on using the NVIDIA app. Okay, now we're going to rebuild with telemetry. Well, first we'll do with logging so you can just see what the floats look like. So I'm going to uncomment out, define log Cuda. So we'll we're only going to look at it for a second, so it doesn't really matter. So we'll build that. And we'll just run it without the monitor so you can just see what it looks like. Oops, wrong thing. There we go. Yeah, here, let's stop that. And so those imaginary numbers turn into something meaningful related to frequencies. Now we'll build with telemetry enabled. And we're not going to use monitor for this because it's not going to perform well because we're doing telemetry. This might take a while. I'll pause the video. While it's running, I'll show you the class that handles it. So there's a global, it's a global class, but it's specific for each run. And so it's going to be the latest run. It doesn't consider all of the runs in the program, just one. So I probably should have just ran one, but it doesn't matter. The class is called signal report, and inside of it, it has a struct called frequency response, and has some vectors of complex and floats and spectrum matrix and so on. And so most of the data works off of magnitudes. And so it computes the dominant frequency, which isn't very interesting in my case because, you know, voltage isn't real exciting. So 0 is going to be the dominant frequency. But anyway, it computes the spectral centroid. And we'll get to that when I show you the graphs. It's spectral spread, the compute power, and so on. And then it does all of that down in that right here. So this report is a method. This accumulate spectrum is a method off of the signal report class that I just showed you. And there's one line of code here, but it does all of the things that I just showed you down here. Here's the accumulate spectrum. So it does all of this, gathers all this data, and then it logs it. And we use a special log file for that. I don't have it parameterized. They're hard coded to like an MKL one and a Cuda one. So that's one improvement I could do, but I don't know that you're going to use anything else. But okay, it takes a while. I mean, it just ran 268 million floats, so it has to analyze all of that. Anyway, so then there's a program. So it writes to a CUDA _ analyze report.txt. And so when you run this analyze spectrum report, you have to say CUDA because there's two types. There's an MKL and there's a CUDA. So then CUDA is the argument here. And so you run that. It takes a while for this to come up. Okay, there it is. So spectrogram, it's a visualization of how the frequency content of the signal changes over time. So there's so this horizontal is the frequencies, and the chunks are the time progression. And then the sliver here is the magnitude or the amplitude or power of each frequency at each time slice. This dominant frequency over time, it flatlines at 0. The voltage, my voltage data doesn't really oscillate much. So its dominant frequency is going to be 0 hertz because the frequency is essentially, doesn't move a lot. There's no cycles or pulses or periodic stuff. The spectral centroid and spread, the centroid part, it's It's the center of it's the average of the weighted frequencies, and the spread measures the variance around it, how narrow or wide a frequency content is. Basically, it's about noise. And then power per batch, you can see that with CUDA, the energy increases the more data you push through it. So the lessons learned, at least for me, is, well, I tried to get too cute with the reporting, but I did have to decouple telemetry from perf. There's a new SDK out, but my driver's not compatible with it yet. 13.0, I use 12.9. I'm not sure I'm going to do much. One thing I was trying to push on was trying to get, I wanted to reduce the copying, because you're copying over to the host and over to the device and back to the host. And I wanted to do more on the device side, but wasn't really able to do that so far. So if you have any comments on tips on how to do that, please put them in the comments. And then I might look into like pinning memory and so on. But I'm not like a CUDA expert. So, but this is just what I found to be the most beneficial was increasing the batch size, and then using memory map files, and then batching up all the file handles. So finally, here's some links to the code up on my GitHub repository. Here's about me and LinkedIn, and then if you're watching this video, you have my YouTube video. But if you here's the link to my technology and music YouTube channel. So we've been going for 37 minutes, so I think that's enough. So hope you enjoyed it, and thanks for your attention.